Welcome to the ARMA Student Design Competition 2022 webinar. My name is Jim Hazard at ITASCA, and I'm here with Varun, also at ITASCA. This is just going to be a little bit of an introduction to the software you will be using, and then also the specific problem that you're trying to solve. So just a couple of housekeeping things to get started. This is a webinar, which means that you can't just unmute yourself and speak. So if you have a question, you should be able to ask the question in the question panel, or else raise your hand, and then we can unmute you here and you can ask the question. So the better route is to just type in questions and we can address them as they come up. Okay, so this year we're using FLAC2D, and this is a new program. Probably you've heard of FLAC before, and you may have even used it before. This is kind of a new version of FLAC. It was built to be much more similar to FLAC2D, and also easier and more intuitive and more attractive. And so I just got a couple of slides here about FLAC2D in general, and I'll show some of the basics, and then Varun will show you more about this specific problem. So FLAC2D is a continuum numerical modeling software. So that means in general we're modeling a continuum, but you do have the ability to put in some faults or joints or discontinuities. And in fact, this is one of the things we will be doing with this problem. It uses the finite volume method. You probably have heard a lot of people saying that FLAC uses finite difference. There is a subtle difference here. The finite volume method allows us to create unstructured meshes, so they don't have to be form perfect grids. And this makes it very similar to finite elements. What's different from most finite element programs that you may have seen before is that FLAC2D uses an explicit solution. And what that means is that it sort of marches through time in a pseudo-dynamic way, and it makes it very easy to do dynamic problems and large strain problems and highly nonlinear problems. This is a program that's specifically targeting civil, mining, geotechnical, petroleum engineering. So there are certain features in there to make life easier for people in the geosciences. And mostly we're using this for engineering design, factor of safety. A lot of people use this in research. And, we also do a lot of back analysis. And so just a word of warning here. This is a new, like I said, this is a new product for us, and you are all using the beta version. It's working pretty well, and we're pretty confident that the mechanics and the engine is working well. You may find a few little glitches with the user interface. Again, it's a beta version, and we're happy that you're trying it and testing it. And we would appreciate feedback if you feel like giving it to us. But be aware that you may come across one or two little things that are imperfect here. Okay, so what I'm going to do now is just bring up FLAC2D and give a short little demonstration about it, and just to show you what it looks like before we get into the specifics of the problem. So hopefully you have already seen the, I'm going to start it from scratch just so you can see what it looks like. How do I do that?
So it's in the ARMA template.
I'll just do that. So hopefully you have seen the PowerPoint that tells you about getting a license and setting up a license. The first time you start this up, you'll see this thing that says a valid license will not found, and you can click show a license location and fill in the details there. I'm not going to do that now. You have that information. If for some reason you couldn't get it to work, let us know and we can work it out. So let's pretend I have a license here already. This is the first thing you see when you start it up. And then what you're going to do is make, in the case of the template that we give you, you've probably got a project already, so you can say open project. For this demonstration, I'm just going to show you building something from scratch. So I'm going to say new project. And then I can make a new project, and I'm just going to call it slope. So now what you see is this screen that looks like this. The project is really just a holder for everything that you're doing. So the project will contain data files, plots, saved states. You can see this down the left-hand side. The project itself, again, is just really a wrapper around all of this stuff. And so when you start a new project, it doesn't have anything in it. What you're seeing here is nothing down the left-hand side here, and basically a blank screen in the middle. This is where you're going to do most of your work. At the bottom here, you've got the console, which gives you the information about things that are happening in the model. And then over on the right-hand side here, you've got this control panel, which is now empty because we're not seeing anything. If you start your program and you don't see this control panel on the right-hand side, there's buttons up here to turn that off and on. Because it's possible that the first time you start it, that might not appear. Then you need to press this little button to show the control panel. So now you're looking at this blank screen. What do you do? Well, one thing you can do is go to help. So I'll just show you how the help works. If you go to help, and you go to help, the help actually appears over here in this control panel, which is why I wanted to make sure that you were able to see it. So by default, the help appears over here in the control panel. And what we've got here, if you click on these little arrows or you just make this bigger, there's a whole tree of help topics that you can drill down into and look at. I'm not going to go into it now. I'm just showing you where the help is in case you feel like you want to do that. If you find this little control panel window too small, you can right-click on this and say open in default browser. And it'll actually bring up the help in a browser, which is generally more convenient for looking at these things. Okay, that's the help. The other thing that you can do before you even get started is look at examples. So if I go to help and I go to examples, you can look here under FLAC, and there are a bunch of examples that we give you, and you can just open them up, and you get the whole project with all the data files and everything else, and you can run them and look at them. So I'm just telling you where they are in case you feel like you want to do that. But what we're going to do is create a new example from scratch here, just a super simple example to show you the workflow. Okay, so I'm going to hide this help. I don't need that anymore. And what you would normally do is you need to draw some sort of geometry. And the easiest way to do that is to start with a sketch. So if it's telling me here in the middle, use the pull down menus to manage this space. So I'm going to go to this pull down menu and I'm going to say, give me a sketch. So now I've got a blank sketch screen and I'm still wondering what I'm going to do. All you have to do is click on it and it says, create a new sketch set. It's possible you could have multiple sketches. In this example, we'll just make one. So we're going to have a sketch called slope. And now you can see something that is probably familiar to you, just a way to draw something in 2D. You've got a grid. Your mouse will snap to the grid. You've got ruler. You've got axes. We know that 0, 0 corresponds to the intersection of these lines. So it makes it relatively easy to draw shapes in here. By default, as soon as you start the sketch, you have this little tool which allows you to draw lines. You can see the two little dots with a line next to the cursor. And this allows me to draw lines here. I can choose other shapes. So if I go to this drop-down menu up here, I can make a circle, I can make a rectangle, I can make a polyline. So it's relatively easy to make simple shapes here. The other thing you can do, which is very common, is to actually import something that you've created in another program. So there's a button here that says import background image. You could actually import a DXF and just turn that into points and lines and use that to create your model. We won't do that here. What we're going to do is just draw a simple slope. So I'm going to start with a rectangle. So I'm going to choose this rectangle option. I want to zoom out a little bit here. To zoom in and out, I use the mouse wheel. Right? So the easiest way to zoom in and out is just to use the mouse wheel. And I'm going to draw a rectangle that goes from 0, 0 here. I don't need that much. 0, 0 to 60, 30. There's my rectangle. Now maybe I want to put this more in the middle. If I click on this again, it's going to draw another rectangle. Instead, I just want to select things or move the plot around. I need to click on this little arrow. So this tool is the drawing tool, and this arrow is the selecting tool. If I click on the arrow, now I can click on things and get information about them. You can see over here on the right-hand side, and I'll talk about that in a minute. But this also allows me to manipulate the plot a little bit. Again, I can zoom in and out with the mouse wheel, and I can move this around by holding down the right mouse button and then the left mouse button and then moving it around. So this is mostly what you need to know. Zooming with the wheel and moving around with the right mouse button followed by the left mouse button. And that's how to manipulate these plots. So now I've got my rectangle here in the middle. It's time to draw some sort of slope. So in this case, I don't want a rectangle. I just want to draw some lines. So I go to line here. And I'm going to draw a line from 4030 to 2010. It's actually possible to type these numbers in. But since it snaps to the grid and I want nice round numbers, it's relatively easy to just draw them. And then I'm going to draw a line across the bottom here. And there's my slope. If I made a mistake and I click the wrong spot, there is an undo. I can go up here to edit, undo. And it gets rid of that line. And then I can draw it again. Okay, so there's my slope. Now, in theory, I could just mesh this. Let me click on the selector tool. If you look at these red X's here on the boundaries, that's telling you where the zones are going to go, where the zones on the boundary are going to go. So if I hit this A, it will automatically mesh this. And I get this relatively coarse mesh. But it works, and it's great. And the reason for showing you this is that, again, with FLAC2D, it does not need to be a structured mesh. If you have complicated geometries, you can just hit this A, and it will fill in the space with some sort of automatic mesh, which is not necessarily perfectly structured, as you can see here. Let's undo that. I could also increase the, if I click on the select tool, I could increase the density of the zones on these edges here. So I could click on this edge, for example, and it's telling me there are 4 zones there. I can just increase that. And then if I hit the A again, I'm going to get denser zones around here. So in theory, I could go along and have a lot of control about the zoning on these different edges. I'm going to do something different to that. So I'm going to undo that, and I'm going to undo that. Even though it's possible to make these unstructured meshes, it's still better to have a structured mesh. You generally get better results. And for a simple problem like this, it's relatively easy to make a structured mesh. All you need to do is create 4-sided shapes. So to do that, I just need 2 more lines here. I'll draw one from here down to here, and one from here down to here. Oh, see, I missed there, so I'm going to undo. One little trick is if I hold down the control key while I'm drawing a line, it makes it perfectly horizontal or perfectly vertical. There we go. So now I've got all 4-sided shapes. If I click that A, I get a nicer looking structured mesh here. I want this to be more dense than this. I want to have a higher resolution. And again, I could go along and click on all these edges and change the zone length. But an easier way is to do it globally. So I can click on this little picture of the grid here and specify the zone length in the model or various other things, the total number of zones or the number of zones across the longest extent. I'm going to choose a zone length of 2. I'm going to say OK. and it remeshes it and gives me something that looks a little bit nicer. So that's it for my mesh. There's one more thing I can do here in this sketch pane. I can assign names to the different parts of the model, and we call this groups. And this is super useful later on, because what we're going to do later is excavate this top left portion and leave behind this slope portion. And so being able to identify this top left portion is useful. So what I can do here is to select all the parts of the slope. And then up here under sketch, it says group, I can give them a name. And so I can just call it soil. And then I could select this part here that we're going to excavate, and I can just call it air. And so now the different parts of this model have different names. And I'm basically done with this sketch now. I've built my mesh, I've assigned some names. Now I just need to turn this into actual zones. So I press this little button here with the arrow that says create zones. And there's my model. So this now automatically opens something called the model pane. So we were in the sketch. See, if you do this drop-down menu, you can see the different things going on here. The sketch is where we just were. And as soon as you create the zones, it brings you to this model. In this model pane, you can also click on things and give them names. But we've already done that, so we don't need to do it again. Other cool things, though, that you can do is click on things and assign constitutive models. So if I select all the parts of this model, and I go up here, see, here's where I can assign a group name, but I can also assign a constitutive model. So if I go to standard, I can choose, for example, more Coulomb. And everything gets the more Coulomb model. And once I've assigned a model, I can then go in here and assign properties. So it knows that it's the more Coulomb model, and it tells me what properties I need to fill in here. So I'm going to put in Young's modulus, 27, Poisson's ratio, 0.25, cohesion, 1E4, friction, 35. Now you'll note here that it doesn't tell me anything about the units I'm using. In FLAC2D and all the ITASCA programs, you don't necessarily have to specify the units. You just have to be consistent with the units you're using. So here, I know in my head that I want to use pascals. And so my Young's modulus is 10 megapascals, and my cohesion is 10 kilopascals. As long as you're consistent and all your stress units are using the same thing, then it's fine. I could have done the whole thing in kilopascals and just divided these by 1,000, and it would still work. Again, as long as you're consistent with your stress units, it's all going to work out. So in this model, I'm using pascals. I specified these properties. I say save changes, and I'm done. So I've got my grid. I've got my group names. I've got my constitutive model, and I've got my properties. Now is a good time to actually save this model. I encourage you to save occasionally while you're doing this. Now there's two things going on here. There's the project itself, which is holding this sketch and the model pane and everything else. And then there's the save state, which is the zones and all the information associated with them. So if I just say I want to save my project, that says, great. You also want to save the model state, which is essentially all the zones. And I say, sure. And I need to give that a name. So I'll call it, I don't know, geometry. So now you can see inside of my project, I've got a save state over here on the left-hand side, and I could double click on it and bring that back anytime I want to. If I go forward and make a bunch of mistakes, I can just come back and double click on this and get back to this state. So this is everything I can do with the sketch pane and the model pane. From here on out, we're going to have to type in some commands. So what I need to do is create a data file. So I go File, New Data File, and I can just call it Run. And what this is basically just a text editor. Okay, And again, you can see the data file has appeared over here on the left-hand side as things that are inside of my project. And I could have multiple data files. In this example, we'll just have one. In the example you're getting later, I think there's more than one. So here's where I need to start typing commands. When you get the template for your project, you will already have a data file that already has commands in it. And that's often a good place to start, just modifying something that already exists. For now, for this example, I'm just going to show you how to do it from scratch. Now, we've already set up the grid and the properties and everything. And so what I want to do is start by restoring that. So I can say model restore geometry. Now, maybe you can't see this font because it's so small. This is just a regular old text editor, so you can change all these options here. If you click on this little button with the check mark, I can change the background color and the foreground color and the font and all that stuff. So I'm just going to make my font bigger so you guys can see it. Right? So now you can see this command that I just typed in. I'm restoring that save state. Now let's pretend I have a command, but I don't really know what it does, or I'm not 100% sure about the syntax. That might be the case when you get this template. You can click on this command and press F1. In theory. There we go. And it brings up the help section about that command on the right-hand side here. So now you can see that it's telling me what this command is actually doing and what keywords it's looking for. It's looking for a string. So this is totally useful, especially when you get the template. Maybe you don't know what all the commands are doing. You just click on it, you press F1, and it brings up the section of the help. Okay, so I've restored my state. The assigning of the properties that we did before didn't include density for some reason. This is something that we'll fix as we go forward from the beta version. But for now, you have to specify the density with a command. We need to turn on gravity. So what you can see here is there's two types of commands. There's things that act on the whole model. So I'm restoring the whole model, or I'm specifying gravity for the whole model. And there's things that act just on zones. So I'm specifying the density for just zones. So pretty much all these commands start with either model or zone, and then you're acting on those things. So I've restored the model, I've set the zone density, I've set the model gravity, and now I need to set the initial stresses in the zone. And I can just say zone any stress. And this will work out the initial stresses due to gravity in those zones. And there are a bunch of things you can do, like change the horizontal stresses and so on, which I won't get into. But again, if you just hit F1, it'll tell you about all of the things you can specify here. Okay, so that looks like we're almost ready here. We've got the properties, we've got the geometry, we've got the density, we've got gravity, we've got the initial stresses. If I now run it, what will happen is the whole model will just fall down through the floor because I don't have any boundary conditions. So the last thing we need to do is fix the bottom and the sides so that this thing doesn't fall down through the floor. So I can say zone grid point fix. And on the sides, I'm just going to fix the x velocity. And I need to give a range to specify the sides that I'm acting on. So I say range position x0 is the left side. And then I can just copy and paste this and do the same thing on the right-hand side. And on the bottom, I'm going to fix x and y. So I can just say, instead of vel x, I say velocity, and I give, just vel, sorry. And position y 0. Now we're ready to solve. One more thing we have to do is tell it whether we want a large strain analysis or a small strain analysis. Most of the time, you'll probably be doing small strain. So we can say model large strain off, and then we say model solved. And once you have everything typed in here and you're happy, you can press this little green button to run it. This will automatically save it and then run it. There you go. It's done. Now it's done something, but we need to make a plot so we can see what happened here. So we can go up to here, right? So now we've got our data file, the model, the sketch. Now we need a plot. So we go new plot, name. I need to hide the help here so I can see the controls. So now, again, I've got a blank plot. I need to plot something. You go to this little plus over here. You click on that, and there's all the different things that you can plot here. Most of the time, you'll start by plotting zones. So what you want to do is go down here and look for zone, double click on that, and it plots your zones. This, by default, shows you the same thing that we saw before, the zones colored by the groups. We now want to check if our initial stress state calculation worked okay. So instead of showing these solid colors, we want to show contours. And by default, the contours are showing displacement. We can choose different things here as well, stress, strain, properties, and so on. But for now, displacement is fine. So you can see here the displacement, the maximum displacement is about 1 millimeter, which is very small, which is great. That means everything is balanced and things didn't move very much. We could get a little bit more detail here by putting vectors on here. So if I go to this plus and I choose vectors, I can get vectors of displacement. So I can see there's a little bit of downward motion here and a little bit upward here, but it's millimeters, so we don't care. Over here on the right-hand side are all these controls. So if I click back on my magnitude plot item, I can do things like, if I go to contour, I can do things like change the color scale, change the maximum and minimum, reverse the colors. And so there's all kinds of control you have over the plotting over here on the right-hand side under the attributes. Okay, so that worked. It's not very exciting. What we want to do now is just delete this part here and see what happens to our slope. So I need to go back to my data file. I can just go over here under data files and double click it. And I can say zone delete range, range group air. I think I called it air. Now, one cool thing you can do with FLAC2D is you can actually watch what happens on your plots as it's doing the calculation. So what you might want to do here is actually split this screen so I can see the data file and the plot at the same time. So I can click on this little split thing here and say split right. And in the right-hand plot here, I can just double click on the plot. And there's my slope plot here. So now I can see the data file and the plot at the same time. So if I click back in the data file and hit the green button, it's just going to run it again. There we go. So it deleted my.
Solve the model solve as well.
Oh, I forgot to solve it. Thank you, Varun. It deleted it and nothing happened because I forgot to say solve again. There we go. Let's try that. Okay, cool. So now we get something sensible. We deleted the slope. We removed all that material, and everything tends to move upwards because all that material is now gone. And so you get this sort of uplift. And now we're getting like, what is that, 60 centimeters of displacement here. So something a little bit more significant. This slope is clearly not failing. I mean, it just rebounded. There's no sort of failure surface or anything like that going on here. The next thing you might want to do is, the next thing you might want to do is then see how far away you are from failure, or another way to say that would be look at the factor of safety. And so then I can just say model factor of safety. And what this will do is automatically run this thing and let's just run it. I can speak while it's running. What it does is it weakens the material and then tries to solve it, and then weakens the material more and tries to solve it, and then weakens the material more and then tries to solve it. And it tries to find the point just on the boundary between stable and unstable, or failure and not failure. And the amount that it had to weaken the material to get to that point is your factor of safety. And so you can see in the information down here at the bottom, it did the analysis and it's telling me my factor of safety is 1.06. I don't know if you can see that. I can make this font bigger. So this slope is pretty close to being unstable. And what it does when it does this factor of safety analysis is it creates these extra save states for you. So the stable state and the unstable state and the initial state. So if I just double click on the unstable state, I can see what's happening here. I'm getting this expected sort of circular failure and this disastrous slope situation here because it's weakened the properties enough to cause this failure. You can see now the displacement is like more than a meter. And in fact, if I can keep running this, it will be even more than that because this is not stable. It will just keep on moving. So that's basically it for my small example. I'm just going to summarize here and then I'm going to pass over to Varun. I don't know if there's any questions. Now would be a good time. Be aware that this was like a 20-minute overview of something that we normally take like a full day to do in our training courses. So undoubtedly you have a lot of questions. Feel free to, write us specifically or even use the forum. Hopefully you got information about that. The forum is a great place to put stuff down and get answers from people. So I'll just go back to this so I can summarize here. So the normal workflow would be something like this. You start with a sketch where you draw something. It automatically takes you to that model pane where you can set the constitutive models and the properties. Then most likely you will need a data file where you set the boundary conditions and the gravity and the initial stresses. And then you run it and you can make some plots. And so this is this sort of 4-part workflow. In the example you're getting, you probably don't even need the first 2 parts of this because the data file does it all for you. But those parts are there if you want to play around with making your own models. And then again, normally we do a 3-day training course on this. So 90% of the features I haven't talked about, but this is just a list of all the features that are in FLAC2D if you're interested. There's dynamic analysis, there's large strain analysis, there's fluid flow, there's thermal, there's creep. There's the joints and faults that you're going to talk about here in a minute. There are structural elements, and by that I mean liners and bolts and soil nails and stuff like that. A whole lot of different constitutive models and some other things that we don't have time to talk about. And I'm basically done here, and there's a question that just popped up. Oh, we see our go-to webinar. All right, thanks, Andre.
Okay, I think there's another question. No, that's just Andre.
All right, how do I get rid of this? There we go. I'm done talking now. I'm going to pass it over to Varun, who's going to talk about your specific problem.
Yeah.
Sound good?
Okay, thanks, Jim. So now we are going to actually talk about that specific template that we gave you for this problem. So we didn't want you to learn the software from scratch if you haven't used one of the ITASCA codes before. So we provided a template so that even if you haven't used the code before, you can use the template, make a small changes here and there, and actually run a model and work on the problem for the student design competition. One of the things, I don't know if you paid attention when Jim was creating that model, was that at the time when he was clicking and sketching all those things out as well, there were kind of commands being generated right here, which were replicating exactly what he's doing up in the sketch pane and the model pane. So that's kind of one of the nice things about all ITASCA codes is they have graphical user interfaces, but in the back end, everything then translates into a command. The benefit of that is it's very easy to set up parametric models, which can allow you to do slight variations in geometry or model properties or other things, which then you can run very quickly and do a lot of sensitivity analysis very quickly. And we kind of make use of that fact when we set up our template. So I'm going to restore our template now. So basically, these are the files that you should have received. And if I start FLAC2D again, and if you go and do open project instead of setting up a new project, and then select that tunnel template, then you would get something like this. So in this case, I have already created 2 plots for you that you can look at things. And then I've already created the model for you using different data files. And I kind of split the data files in such a way, or split the commands in the data files in such a way so that they give you a break at a good point where if you want to manually go in and make more changes, you can actually do that. So if I'll just go back and quickly just show what all the data files do, and then I'll actually walk through the data files and show you how things go there. So these are the files. So the very first file is 0_geometry.dat, and I kind of named them in the order in which you would be running them. So geometry.dat essentially just contains a function where you can define model geometry parameters in a function. And what it does is it calls us the sketch.dat file to generate the sketch. So you don't have to manually go in and generate the sketch. You just specify the points and it'll automatically generate the sketch for you. I mean, you are free to change any of these files and modify them to make the model better, but we kind of provided a basic template for you to have something to get started with. And once you run this file, you can go to the sketch mode and manually change the sizes of zones or the extent of the finer zones and so on before you run the next file. So let's just take a look at that. So here is my model, and this is, so if I just go and click on 0_geometry, that will bring up the geometry file. And here is my function. So essentially the model new just creates a new model, and I define a function in Fish is the internal programming language, and I define a function in that called geometrical parameters. And anything which is followed by a semicolon is treated as just a comment. So FLAC is actually not going to read that. It's just for your own reference to know what you are doing there. So I try to put comments in this entire template so you know how we are setting up the model. So the first comment is, yeah, we are assuming the ground surface is at y = 0, and then here's the function to define the geometry parameters. So the first parameter is what I call is yf_, and that's the location, the y location of the fault. So based on the problem that you got, that's supposed to be at -56 meters. And then t radius is the tunnel radius, which is 3 meters here. And then this is the location of the tunnel where you want to put it. And I put it at -61 just to start with. And then where do you want to truncate your model at the top and the bottom? So I put it from -40 to -80. You can go bigger model. The thing is, the bigger you go, the longer it takes to run. But this is still a very fast model. So most laptops, this should run in a couple of minutes at best. And then on the sides also, you can define how much bigger you want to go on each side. So this is that parameter. So I have 20 meters on each side. And then I also kind of put in a nicer modification to allow finer zoning around the tunnel and the fault. So you can specify how much further away from the tunnel do you want a fine mesh. And I put 5 here. So 5 meters around the tunnel is going to be a finer mesh. And then you can specify the default zone size you want to use, and I'm using 0.5 here. I'm actually going to change this to 1.0 just so that we can run the model quickly. And then the zone size in the densified region, I'm using 0.5 here. So the finer zone size would be that. Again, once you run this, you can always go back in sketch mode and change this as I'll show here. Then I put a parameter, are you modeling fault 2 as well here? You can just say true or false. For now, I said false. And the second is if you are modeling it, then you should put a location for the second fault, which is here. Next, you don't need to change any of these numbers. All I'm doing here is just declaring a few more variables, and then I use those numbers to actually create the model. So this is just a tolerance for assigning conditions. So, plus minus that much, use those conditions. And then, just define the left extent as minus of that, right as plus of that, and, left and right extent of fine mesh and so on. And then, as you can see here, it goes and calls sketch.dart. So right now here, I also call one model.dart, but if you want to make changes to the sketch mode, just comment it out and it wouldn't call the one model.dart file, which does the next step. So only call sketch.dart if you want to make changes. So once you have this ready and you have put in the parameters that you want, you can just hit enter or hit this green button and it'll run that. I'll just quickly show what the sketch mode does. So basically sketch mode, what it really does is it creates points. So it created 4 corner points, 1, 2, 3, 4, and then it connected them by edges. Then it created 4 points in the middle where the tunnel is supposed to go. And then it also connected those by edges. But here, instead of using a simple edge, as Jim was showing, we used an arc to connect those. And then I put control points on those so that you can define the shape of the circle. Then I added a fine resolution box, again a rectangle, a center line to split it through, 2 lines for the faults, and that's pretty much it. And then change the zone size in the densified region. So basically I said zone length is changed to the finer one in that range that I want to. And these are just some meshing parameters. So I'm using an unstructured mesh here. If you do decide to change the mesh in the sketch mode as Jim showed you, you can just comment this out and actually use a structured mesh, which is even better. Mesh gradation just controls how quickly zone sizes change next to each other. So if this is a smaller number, then the zones are more uniform in size and then they gradually change sizes. If this is a bigger number like 1, so it's between 0 to 1. So if it's closer to 1, then you can have abrupt changes in zone sizes when it does automated zoning. And then mesh optimization, 1 to 10, like how much time you want to spend optimizing the mesh. You can use just 10 for this because this is a relatively simple model. It's not going to take much time. And then shape quality is again 0 to 1. It's also a function of how nicely shaped zones is the program going to try and put, which will take more time the higher this is. But again, this is a simple model, so it's not that big an issue. So you can keep it at 1. So we run the model. So I'm just going to create a new plot and just show you how that looks like. Well, actually, we can just go to sketch because we didn't really create the zones yet. We just created the sketch right now. So I go to sketch. Here is our model that we created. So that bigger box, the tunnel, the single fault, a box further, another box around it for finer zoning, and then I just kind of split the tunnel also in the center. And again, if you wanted to change zone sizes anywhere, you could just click on it and you could change here the number of zones that go in here, or you could change the length of the zones that go in here. So once you are happy with this, then you go to the next file, which is number 1 model.dart. And what this file does is it creates zones from the sketch, assigns the groups to the rock and the tunnel, like Jim showed you for the slope and the air, creates the faults by actually creating a split between the zones where the fault is supposed to be, and then just saves that as one model.save, which is basically includes all your zones with everything assigned. And again, I'm calling the next file right here. But if you don't want to do that, you can just comment that out and manually call it as well. So now I'm going to just hit this green arrow button and let it generate the zones. And if I go to the model plot, now you'll be able to see all the zones generated. So you can see all those zones being put in here. I could create another plot just to show how things look. So I could go create new plot, and I don't know, I'll just give it any name. Just not the model, maybe just geometry. Then go and add the zones here. And here in the color, right now they're plotting by group, but any group, any slot in the group. If you remember when we were in one, when we assigned these groups, we assigned the group in a slot called excavation. So think of the slot as kind of like a tag or a label that under that label I'm filing this is rock and this is tunnel. So if I go back to geometry and under zone groups, instead of any slot, if I go pick the excavation slot, you can see everything is here is rock and this is here is tunnel. And anytime you actually hover your mouse, there is an information zone here on the right hand side. So it will give you all the information about where your mouse is. So right now you can see it says plot item 1, that's the zone number. So that's the zone that you are right on. And it says what face number it is, what's the group in that zone, what's the nearest grid point, and what's the nearest face, and what's the group name, which is labeled rock there. So you can query the model that way as well, or you can use this arrow with the question mark and then click anywhere, and then it'll give you the option. And I could say, okay, I want to know more about this zone. So it'll show you all the information. It's a quadrilateral zone. These are the groups that are assigned to that zone. These are the stresses in that zone, and so on. And you could copy it to clipboard and then copy it somewhere else. Okay, so now we have the geometry. Then the next thing, and so we are following a similar workflow as Jim showed. So these should be relatively quick to follow. So then we restore that one model save, and then we assign more Coulomb properties to everything. And then we assign the material property. So instead of using the model pane, we are just typing them in here. So this is the bulk modulus, shear modulus, density, cohesion, friction, and tensile strength. And if we wanted to give different properties to top and bottom, I could put a range and say, give these properties only to the group top rock in geology, because we assign that way as well. But we are not doing that because we are assuming same properties for the entire range. And then next we assign fault properties. So those are assigned using zone interface node properties. And so we have a normal stiffness, a shear stiffness, friction angle, cohesion, tensile strength, and again we give a range. So this goes to fault 1 because we are assigning this around YF, which is the location of fault 1. And if there is fault 2, we assign the fault 2 properties the same way as well. For the purpose, so we did in the problem provides you with cohesion and friction and a coefficient of variation. So for the stiffness of the rock, you can assume a reasonable value that you would expect for that type of rock with those kind of values. And for the fault, you can assume that the fault is stiff enough not to play a role in so that the stiffness doesn't play a role in the response, and you can actually use a fault stiffness which is high enough. And by high enough, we can specify the normal stiffness and the shear stiffness by the same way. So if you have the bulk and the shear modulus of the zones around it and the size of the zone around the fault, if you calculate this expression and multiply that by 10, anything larger than that would be sufficient to make the fault like stiff enough so that the stiffness doesn't really come into your solution as much. So you assume fault is stiff enough, and as soon as the stresses reach the threshold, it's going to slip. The next thing we do is we assign roller boundaries on the side and fixed boundaries at the bottom. So here we are doing the same thing, fixing velocity on the left side, fixing velocity on the right side in the x direction, and at the bottom we are fixing velocity in the y direction. All right, we could also fix velocity in all directions, remove this y and just say fix velocity in all directions. And I'm assuming since the tunnel is deep enough, if you don't want to model all the way to the surface, if you truncated your model somewhere in between, like we truncated 40 meters below ground in this case, then we need to apply the stress that's coming from the top. And we use that as the boundary condition at the top, where we apply that stress that would be at that level. So that's done using zone face apply. stress YY, and then I just so another nice thing is if you use square brackets, you can do calculations on the fly. So I know my density I'm using is 2600. The gravity I'm going to use is 9.8. And I know that the location of my upper part of my model, which I gave a variable named YU. So I can just calculate right here what is the stress that should be there, so that I can just specify that right there basically. And so that would basically put that stress there and kind of hold that boundary in place with the stress. And then I give that the range as position Y, where equals to YU, which is where my top of the model is. Then I turn on gravity. And also, if you remember in this model, we have water table above the fault as well, the fault kind of acting as a barrier. So I initialize the density of water, and then I assign the water table using a water table or the plane as a plane command. And then I can give a range only up to which point those pore pressures should be applied. So I say zone water, and then I say plane origin. So origin is at 0, 0. So because I assume the water table is right at the surface. Normal 0 minus 1, which means that's the direction of gravity, which is going down in the y direction. And then where should the pore pressures be initialized? Only from the top of the model, but only till YF, where basically YF being the fault, because I don't want pore pressures below the fault because the fault acts as a barrier. So that puts in pore pressures. Then the last step is just initializing the stresses. So that's the same zone initialize command. You will see I put in a couple of more keywords here. So basically the total keyword means that when I'm going to when this command also calculates the horizontal stresses, then those horizontal stresses will be calculated using total stresses and not effective vertical stresses. So then you can, if you don't put this command, then by default, it'll calculate horizontal stresses using effective vertical stresses. Then the ratio is the ratio you want to use for horizontal stresses. So I put the value 0.4. If you want to use different values for both directions, you can put two values one after the other, and that would go in the other two. So there'll be different horizontal stress coefficients in each direction. And then since in this case, we know that the top of the model does not correspond to ground surface, we have to put an overburden stress, and that is the same as what we used in our boundary condition, which is this. That's pretty much it. Then we turn large strain off and we solve the model to get the initial state. So I'm just going to comment out 3 excavate so that we can just run this part. Okay, it's going to ask me for a key. So I'm just going to brief for a second. And there it is done. So now if I go to the model, here was my model. I can actually, instead of label, I can go to contour and I can actually plot displacement. So you can see displacements are very low here, 10 to the power minus 4, minus 5. And instead of displacement, I actually want to plot stresses. So I can go and plot stress, and I want to see stresses in the YY direction. So here is how stresses look in YY. If the contours look a little bumpy right now, that's because I'm not smoothing them. I'm just painting each zone with the color of the stress in the zone. So if you want to do interpolation, then you can just choose volumetric averaging so that it actually does the interpolation as well, instead of just coloring the entire zone with just the color for that stress in there. And then you can see the contours look nice and clean and horizontal lines. I could create another plot item right here with the zone, and instead of, again, choose contour, and instead of stresses, I could do check pore pressure now. So if I go check pore pressure, here I can see that the pore pressure is assigned as well, but it kind of ends at the fault. So below that there is no pore pressure. There's pore pressure above the fault, but nothing below the fault. So that is all for setting up the model, and everything that I kind of talked about, I kind of summarized here in the slide as well. So, and I will mail these slides, or we'll post them on the website as well, just so you have them for reference. And then the last thing is excavating it. So before we excavate, though, so now that's the 3 excavate. What I did is actually zero out the displacement. And the reason for that is, even those displacements were tiny, I don't want, when I look at if I want to look at displacements only from the excavation, I don't want to look at anything displacements that happened before. So I'm just zeroing them out. But this only zeroes out displacements, doesn't affect the stresses or anything. This is just kind of cleaning the slate there so that you can see what additional displacements happen from that point onward. And here I'm setting up a few histories at a few locations if I wanted to plot the time histories to see what happens as the model is solving. So I'm putting one history right at the top of the model, where just to see, if how much deformation is coming all the way to the top of my model. And I'm putting one history in y direction right at the crown of the tunnel so that I can see how much deformation happens there. Now, to remove the tunnel, you can do a bunch of things. You could either just take everything out in one shot, or which is this zone delete range group tunnel command. So you're deleting everything, which is the group tunnel. Or you could slowly reduce the stresses to model the face of the tunnel reaching this location in 3D. And for that, you basically would create a relax command, which is zone relax excavate, give it a name, specify a ratio, how much should it solve to for every increment, basically. So it slowly releases the stresses a little bit, solves to not all the way to equilibrium, but to a level that you want to. So typically FLAC2D uses 1E-5 as the tolerance. So we use a little higher tolerance here. You can play around with this as well. Just don't go below your global tolerance. And then you can specify minimum, which is when should it stop. So if you put 0, then it'll remove all the stresses, then delete the zones, and then stop. If you leave it at like 0.1, then it will stop when the stresses have reached 10% of the original value, and then you can take it on from there. So that can be useful if you are applying some kind of pressure or anything else inside the tunnel or something like that. And then once this is done, you just solve to equilibrium. One other thing I did is, actually, let me just solve this to equilibrium. And while this is solving, I will, okay, it's solved. So, and while when it has solved, so if I go back to geometry, and here it has solved, if I wanted to actually look at what the stresses in the interface look like, I could go add a new plot for an interface. And instead of location, I use contour, and I could choose either normal stress or shear stress. And here you can see the contour of shear stresses on the interface. So, and if you move your mouse over them, it'll show you basically the location, and you can interpret the color as well. So this might be a little difficult at times to manually go and inquire each stress. So we write a small fish function here, which basically does that for you automatically. So what this does is, this is a fish function called interface stress, uses these 4 tables to store all the data, and it basically loops through all those interfaces, stores their X location and the normal and shear stresses. So here is what's going on. It says IT equals to interface find. So it basically finds the interface, which is fault 1. And then for every node in that interface, it finds the position. So these are all kind of intrinsic functions, which is why we put them there to make your life a little easier to start with. And then it puts the normal stress minus the for pressure. So basically the effective normal stress in table 1. And in table 2, at that location X, it puts the magnitude of shear stress. And it does that for fault 1 and stores that in table 1 and 2. And it does that for fault 2 and stores that in table 4 and 5. And then at the end of it, when we give this command, which is the name of the function, it just runs the function. And then we can export those tables as comma separated value files. So here I'm just exporting each one and giving it the name as the name of the file, whatever I want. So file 1 has fault 1 normal stresses, file 2 has fault 1 shear stresses, and and then yeah, fault 2 norm, and then this has fault 2 normal stresses, and this has fault 2 shear stresses. And that's about it.
You can plot them too.
Yeah. So here, when I go to stress tables, I have them plotted. So if you wanted to see how to plot them, you could go to add another item, go to tables, and I'm just going to turn off this interface shear stress. In the tables, I can click on plus, and that will plot the fault normal stress. So on the x-axis is the x location, and the y-axis is the stress. And if you want to see individual points, you could even open this up, instead of line, put both marker and the points. And I'll increase the marker size so you can see where all is it picking up those. Okay. I think do we have any questions? I think that's pretty much everything I had.
There's one question, which is, I wondered if you could have the tunnel script. I assume they're getting these scripts, or they have them already.
Yes. So all of the scripts for this template was actually emailed to the teams. So in case if you haven't received that, I would say you just reach out to the organizers, and we'll be able to email you again. So a link was emailed that you could use to download the entire template. Okay, so another thing, so this was basically the stress tables, and here I kind of plotted 1 and 2. So basically the normal stress and then the shear stress on the same plot, just to show you how it looks like. We can create other plots too, like in this plot, I actually created a plot of the state of the zones. So then I can see here where the zones are failing. So here the zones failed. P means past and N means now. So these zones here are failing in shear now, and had some shear in the past too. These zones had some tension developing here in the past. Everything else stayed pretty much elastic. So you can you can look at stresses. You can look at state of the zones and query the model to make sure everything. I think that's everything we have. For those of you who actually are good at Python as well, there is Python integration, and Python, you can use Python to control and drive the software as well, which allows you to run a lot of cases without manual intervention. But we are not going to cover that in detail. If you have questions about that, I would encourage you to follow the help or post on the forum. Okay.
All right.
Thank you, guys. Thanks. Bye.